Welcome, class. In this video, we will go over lesson 9.4, the review for mastery worksheets. In this lesson, we will be reviewing how to identify linear, quadratic, and exponential equations. Before we start, let's do a quick review first. The first type of equation is a linear equation. When we graph this, of course, we just see a straight line. A typical linear equation will follow a simple pattern. Like a little XY table here. Say we have values of 1, 3, 2, 5, 3, 7. Now these are XY coordinates. We could always graph this on an XY Cartesian coordinate plane, but we don't always have access to a graph paper, or sometimes it's just not practical trying to graph points, especially when the points are very large. Now, if we have a linear equation, we just look for a first order constant difference. Oh, let me add here. The x-coordinates need to have a constant rate of change. If they don't, we have to adjust the formula. We have to adjust how we determine whether there is a first order difference. But all our numbers that we're using in this lesson are going to have the same rate of change on the x's. So we'll just check the y's. To go from 3 to 5, we are adding 2. To go from 5 to 7, we will add another value of 2. Note that the 2 is the same value already, so we don't have to continue on any further. This is a first order difference, and this will qualify as a linear equation. The other type of equation is a quadratic equation. Here, of course, we have a parabola. There's a parabola shape. A table of values for a parabola may look something like this. 0, 1, 1, 2, 2, 5, 3, 10. Let's do one more point, 4 and 17. Now, a parabola has a second order difference. Again, the values on the x have a constant rate of change. To go from 1 to 2, we will add 1. To go from 2 to 5, we will add 3. To go from 5 to 10, we will add 5. And from 10 to 17, we will add 7. Note on the first order that all these values are different. We have a 1, a 3, a 5, and a 7. Now, if we go to a second order, let's see what happens. To go from 1 to 3, we will add 2. To go from 3 to 5, we will add 2. And to go from 5 to 7, we will add 2. Now, these values are all constant, the same value of plus 2. So it is second order. Second order. Now, these values could have all been a plus 3 or a plus 4 or all plus 5. As long as the values are the same, it does not matter. It qualifies as a second order difference. It does not have to be a 2. It could be a plus 3, a plus 4, plus 5, plus 5, plus 5. Now, the third type of equation we learned are the exponential equations. Values of an exponential may look something like this. Let's do one more point. No, exponentials have a constant ratio. A constant ratio, which means we're multiplying or dividing. And if we're going to divide, we'll still call that multiplying. We'll just multiply by a fraction. For instance, if we were dividing by 3, we would call that a constant ratio of 1/3 because we're multiplying by 1/3. Same thing. Now to go from 1 to 2, 2 to 4, 4 to 8, and 8 to 16. Each time we are multiplying by 2. By 2. And this qualifies as a exponential function if we were to graph these points. Now let's look at the homework. On our mastery worksheet, it starts off by giving us some points up here, and it says we could always graph these points to determine what kind of a shape it is, and then we could predict whether this is a linear, quadratic, or an exponential function. Here, of course, we got points here that we can connect to form a parabola, so this is clearly quadratic. Now, the next set of examples, we're actually looking at the x, y values. Note here, the first example is a linear function because we have a constant first order difference. Here's the first order difference each time we are subtracting 3. In the next example, there was no first order difference, but there is a second order difference. So it qualifies as a quadratic function. The last example, there is a constant ratio. We're multiplying by 4 each time. That's a constant ratio. Problem number 1. It says to graph these points. So that's what we're going to do. -2, -4 is about there. -1, -2, which is about here. 0, 0, 1, 2, and 2, 4. Now, if we're going to plot these points based on this data set, it looks like it's going to form a straight line. What kind of model would that be? If you said linear, you are correct. I guess this assignment we're calling a model, so I'll just write it as a linear model. Number 2. Let's plot these points. -1, 4, which is about here. 0, 2, 1, 1, 2, 1/2, and 3, 1/4. Looks like it was not going back up. I thought we were going to have like a shape where it was going to go back up. Instead, it's coming down. If we were to graph this, it's getting closer and closer to the x-axis. Now, is this a quadratic model or is this a exponential model? We know it's not a straight line, so it can't be linear. This is an exponential model. Specifically, it's a decay model. The values are getting smaller. It's exponential, and I'll put here parentheses, decay. The values are getting smaller. In fact, it almost looks like a half-life because each time the y values are decreasing by a half. Now we're going to start looking for patterns. The x's all have a constant ratio. Now let's look at the y values. We are going from 6 to 12, 12 to 24, and 24 to 48. Well, if we add 6 the first time, we have to add 12, and then we have to add 24. That would be a first order difference, and they're all different. And if we try a second order, we would add 6, and then we would add 12. That did not work either. So it's not linear, and it's not quadratic. What else could it be? Well, if to go from 6 to 12, we could also multiply by 2. 12 to 24, and 24 to 48. This is a constant ratio. And so this must be an exponential model. Number 4. Again, the x's all have a constant ratio. Let's look at the y's. Here we are adding 8, adding 10, and adding 12. There is no first order. Let's try the second order. Here we add 2, and we add 2. There is a second order, which makes this set of points a quadratic model. Number 5, a constant rate of change on the x's. Now let's look at the y's. 4 to -2, -2 to 8, -8 to 14. We could subtract 6, and subtract 6 each time. This is a first order, so it is a linear model. Now on the next page of lesson 9.4, we are given now the basic form of the linear, quadratic, and exponential models. A basic linear form follows the pattern y equals mx plus b. We first saw this back in chapter 5. The next is a quadratic model, which follows the form y equals ax squared plus bx plus c. And an exponential model follows the form y equals ab raised to the x. And often the a value we've been doing has been 1. So we may have just seen something like y equals 2 to the x or y equals 3 to the x. An example here is they give us a table of values, or excuse me, a table here of years and costs. So use the data in the table to describe how the software's cost is changing, then write a function. In year 0, which is the first year really, when it first comes out, there's a cost of $80. Now the software, a year later, is $72. 2 years after it first rolled out, it is now $64.80, and by the third year, it sells for $58.32. We made an XY table here, and they try to find a constant difference. A first order constant difference did not work, as we can see here in the example. The numbers are all different. But a second order did. Did it? Oh, excuse me, did not. I saw the number there. It does not work as well. So we will then try the third time, which is going to be a constant ratio over here. Now, how will we go from $80 to $72? Well, if we're multiplying by a constant ratio, that would give us the answer. So we're going to solve for r. This is how we can find a constant ratio. You take the first term, and then you got to count down to the second term. The first term times the constant ratio r would equal the second term. We solve for r. We will divide both sides by 80. So r equals 72 divided by 80. Now this could be reduced by 9. 9 goes into 72 8 times, or excuse me, 8 goes into 72 9 times, because I just realized 9 will not go into 80. But 8 can go into 80 10 times, 9/10. So r equals 9/10. Here they just wrote it with the decimal, of course, as 0.9. So each time we're multiplying by 0.9, this qualifies as an exponential model. It is getting smaller, so this is called an exponential decay. This is a decay. Now they're actually asking you to find the equation, and they always write the standard form, y equals ab raised to the x. We can pick any x and y values from the table. Here they picked the first set of values, 0 and 80. 0 for x and 80 for y. So they substituted here, 80 here, and the 0 for the x. Now anything raised to 0 is 1. So we have 1 times a equals 80. A must equal 80. And then they just go back and plug it back into y equals a times b to the x. And the a was 80. And they just plugged the 80 in, and we found the b to be the constant ratio, which was 0.9. And we leave the x there. So then we can plug in any value for x greater than 0 and calculate what the cost would be in any year. I know that seemed a little difficult, so we're going to do some examples here. Number 6. Let's see. We have to first figure out if this is a linear, quadratic, or if it's an exponential model. 1 to 4, 4 to 16, 16 to 64. It's growing very quickly, so it's got to be either quadratic or exponential. Now, if you think this is exponential, you are correct. There is a constant ratio. We're multiplying by 4 each time. So we'll right over here, the model, it's exponential. The numbers are getting bigger, so it's actually an exponential, I'll put a parentheses here, growth. Now to find the function, we have to go back and write the general form, which is y equals a times b raised to the x. And we're going to pick 2 points for x and y. We already know the b value is going to be 4. Pick the easiest points we can, which would be 0 and 1. So we have 1 equals a times 4 raised to the 0. Now anything raised to the 0 is 1, so this becomes 1. So 1 equals a times 1, and that just means a equals 1. So you're going to write the equation y equals ab to the x now. The function is y equals 1 times the b value, which is 4 raised to the x. I would still write the 1 even though it's not necessary. It just shows that we solved for it. I would still write the 1. Let me erase some of this here so we can continue. Last example, number 7. Each time here, what are we adding or subtracting or multiplying to get from 7 to 10, 10 to 13, and 13 to 16? There is a first order difference. Each time we are adding 3. So it's a linear model. Now let's write the basic equation always when you're trying to identify the equation, y equals mx plus b. And again, we're going to pick points. We're going to pick the easiest points, which is 0, 7. Because we're given a 0 comma anything, we already know the y-intercept. But let's pretend we don't. Let's just plug them in and still solve it like we normally would. Now the first order difference tells us the rate of change. Each time we're adding 3, and that's going to be the slope. The slope. This rate of change for a first order difference here is the slope. Incidentally, if these values were, right now we're adding plus 1, plus 1, plus 1, but these values we're adding 2 on the side for x's, we'd actually have to take the first order difference and divide it over the rate of change of the x for the slope. But these are all plus 1, so it's really just, the slope is just 3 over 1 each time, which is just 3. Now we pick the point 0, comma 7 for x and y. So y here is 7. The slope is 3. The x value is 0, and we have to solve for b. Now 3 times 0 is just 0. So we get 7 equals b, which we kind of knew that. We knew that 7 here was the y-intercept because the x value is 0. So by default, 7 is the y-intercept because y-intercepts always have an x value of 0. We can now write the equation. Y equals 3x plus 7. If you're not sure whether this equation is correct, you always plug in a value. Like if we plug in, let's say 2 here, we should get 13 for y. If we plug in 2 here, 3 times 2 is 6. 6 plus 7 does equal 13. It does. Check. Well, this concludes this lesson.